Let's get right into it. Today's explainer is a deep dive into the invisible world that is literally powering almost every app, website, and digital service you touch every single day. We are tracking the complete journey of data, from that initial brilliant database blueprint all the way to managing the absolute chaos of live data traffic. If you've ever wondered how millions of people can buy concert tickets, wire money, or stream the exact same movie at the exact same millisecond without the whole system just collapsing, well, you are in the right place. Okay, so here is our roadmap for today. 1. Blueprints to tables. 2. Forging database relationships. 3. The heartbeat of data. 4. The transaction lifecycle. And finally, 5. Preventing data collisions. Let's jump right in.
Section 1. Blueprints to tables, from diagrams to architecture. We're starting right in the design phase.
So we have to start by putting on our hard hats and thinking like a database architect. The crucial thing to grasp here is that an ERD, an entity relationship diagram, is really just a map. It shows us the general shape of our data. Entities like a student, attributes like a name. But a map isn't a road, right? To make the database actually functional, we have to pave real roads by converting that visual blueprint into strict row and column tables.
What the architect starts with is this massive, complex web of students, courses, lecturers, addresses. Honestly, it looks a bit like a constellation. But we can't just shove a web into a relational database. It doesn't work like that. We have to systematically break down every single oval and rectangle using a very strict set of conversion rules. To tame all that chaos, our architect relies on these rules. Single-valued attributes, boom, they just become a direct column. Easy. But composite attributes, like an address, those have to be split apart into individual columns for door, street, and city. Multi-valued attributes, like a student having multiple hobbies, actually get moved into an entirely new table to keep things clean. And my absolute favorite is derived data, like age. Actually, scratch that. We don't even store age. It changes every year, so we just store the date of birth and let the system calculate the age on the fly. It's brilliant.
Section 2. Forging database relationships. Building the roads. So our tables are set up. Now we have to wire them together based on how they interact in the real world. The most common road we build is for a one-to-many relationship. Think of one teacher who teaches multiple subjects. To link them, we simply take the teacher's unique ID, their primary key, and drop it right into the subject table as a foreign key. Now every single subject has a little name tag pointing directly back to its specific teacher.
But many-to-many relationships? Those are definitely trickier. Imagine customers who have multiple credit cards, but those credit cards are also held by multiple customers on a joint account. We can't just swap keys here without making a complete mess. Instead, the architect builds a brand new intersection table to act as a bridge. This new bridge table holds both primary keys, which perfectly organizes a super complex web of ownership.
Section 3. The heartbeat of data. The traffic cop arrives. The city is built, so let's pivot.
We need a traffic cop to manage the millions of invisible cars driving on these roads. Think about this scenario. What happens when two people sharing a bank account try to withdraw the exact same $100 from two different ATMs at the exact same millisecond? This right here is the ultimate problem of concurrent access. If the database blindly processes both requests, you're going to end up with missing money, negative balances, and just totally corrupted data.
The elegant fix for this is the transaction. A transaction is essentially an all-or-nothing wrapper around our queries. It guarantees that a logical unit of work, say checking a balance, deducting funds, and printing the receipt, absolutely must succeed together as one single motion. If it can't, the entire thing fails completely. There is zero in between.
To enforce this, the traffic cop leans heavily on the 4 asset properties. Atomicity, like we said, all or nothing. Consistency means the database rules are never, ever broken. Isolation ensures that simultaneous transactions are completely hidden from each other while they're working. And durability? That's the guarantee that once you see a success message, the data is permanent, even if someone literally unplugs the server a second later.
Section 4. The transaction lifecycle, from start to finish. Let's see how a transaction actually moves from an idea to a permanent change.
What's wild here is how simple the SQL code actually is. You don't need insanely complex programming to manage this flow. You explicitly tell the database to start monitoring by typing start transaction. You run your updates, and then you make it permanent by typing commit. You are literally directing the traffic cop using basic, simple commands. Breaking it down, it's just a 4-step life cycle. You begin, which preps the system, you execute your queries, doing the actual math, and then you hit the critical fork in the road. If everything is flawless, you commit the success. If even one tiny error happens, you issue a rollback, instantly reversing all prior steps as if they never occurred in the first place.
Behind the scenes, the database is constantly tracking these operations through 5 distinct states: active, partially committed, committed, failed, and terminated. It might seem a little overly granular, sure, but tracking states this tightly is the only way to ensure nothing becomes permanent until it is 100% safe. Let's compare the 2 most critical states here. Being partially committed means you've executed the very last line of code, but you're just hovering right at the finish line. Your changes are completely invisible to the rest of the database right now. It is only when you cross into the committed state that the operation is finalized, the data is locked in forever, and the system is allowed to actually see your work.
Section 5. Preventing data collisions. Concurrency control.
Even with transactions wrapping everything up, simultaneous heavy traffic can cause absolute disasters if the sharing rules aren't strict. Take the dreaded lost update problem. Transaction 1 reads a balance of $1,000. A millisecond later, transaction 2 reads that exact same $1,000 balance. Transaction 1 subtracts 100, saving 900. But then transaction 2 blindly adds 200 to its initial read, saving 1,200. Because they didn't coordinate, transaction 2 just completely overwrote and destroyed transaction 1's math. That $100 gone into thin air.
So how does our traffic cop fix a lost update? With pessimistic locking. And it is exactly what it sounds like. The system assumes the absolute worst-case scenario is going to happen. So when the first transaction reads the data, it throws a padlock on it. It throws up a roadblock, so absolutely nobody else can touch that specific row until the first transaction finishes and releases the lock.
And then we have the uncommitted dependency, mostly known as a dirty read. This one is super suspenseful. Transaction 1 deducts money, but hasn't committed it yet. Transaction 2 sneaks in, peeks at that uncommitted temporary balance, and uses it to approve a loan. But suddenly, transaction 1 hits a snag and rolls back to the original amount. Now, transaction 2 is out there in the real world using invalid data that essentially never existed. It's a terrifying chain reaction of bad math.
To stop dirty reads called, we apply isolation levels. If you set your database to read committed, which is pretty standard, it acts like a solid, opaque wall. No transaction can ever see another's data until the ink is completely dry and the commit is final. You can even dial this all the way up to serializable, which literally forces transactions to wait in a single file line for maximum isolation.
It's really a beautifully complex dance, isn't it? From the architect meticulously breaking down diagrams into structured tables, to the traffic cop deploying locks and ACID properties to keep everything moving safely. So here's my question for you. The next time you tap your phone to instantly transfer cash, or you snipe that concert ticket at the very last second, will you stop and think about the invisible architecture and the flawless systems operating relentlessly in the background just to make it happen? Thanks for joining me on this explainer, and I'll see you next time.